Hello, this is Thomas WP from the Physics Teaching Podcast, doing a brief narration of my take on measuring the Young Modulus. So first you want to check that your micrometer reads a good 0. Listen for the clicks. I do this a couple of times because the speed with which you spin it does affect the 0, and you want to get a feel for what the correct speed is to get a nice 0. Now on the back of the micrometer there's a little black dot you can see, and that's where you put one of the funny little spanners and you give it a crank to set the 0 or change the 0 if you want to test the kids with a 0 error. Next you want to measure the diameter of the copper wire. You want to do it in 3 places in case the wire is made in a non-uniform way and take a mean. So you carefully put it in. Listen with the ratchet there, and it's just below 27 on the scale. That's 27 hundredths of a millimetre, 0.27 times 10 to the minus 3 metres. Usually I'd have a lesson on micrometers where I give them a range of things and get them to measure them. And in that one I give all the micrometers a 0 error using the little spanners. So we do a repeat, and hopefully it will come out the same diameter if the wire's not damaged, and it is exactly the same. You heard the ratchet there, and we've again got just below 27. It's not gone past the top mark on the horizontal scale, so it's not got to half a millimetre, so that's 0.27 millimetres again. And then a third repeat, and hopefully we get exactly the same thing. Obviously I'm writing this down as I go. Good practice. I say in the podcast I'm trying to reduce faff, and I used to use a clamp and 2 blocks of wood to grip the wire, and I realised recently that you can just put a screw in the plank and attach the wire to that, and that gives a very clear anchor point, very firm, plenty strong enough for this experiment. So I attach the wire and then lay a metre rule at the screw, and at 1 metre I put my vernier scale. That is pretty close to 1 metre, near enough for me, and the scale is made by reducing a photocopy of the ruler to 90%, and then I just cut it out. The students should definitely wear goggles, and I also cover the wire with little bits of cardboard so that if it does snap at the far end and whips upwards, the energy will go into moving the cardboard and not moving the wire into the experimenter's face. For the pointer to work properly, I have found it easier to have the pointer on one ruler just for the height and line it up with the ruler you're using as the scale. But I realised whilst making the podcast that it might be better to photocopy the ruler at 100% and 90%, make the vernier with the 90%, and use the 100% as the scale flat on the board. It would work much better. I'll definitely be doing that next year. I use a very light hanger to tension the wire so I get a nice stretch on the first weight. And you can use a pulley if you like, but it really doesn't make any difference, I find. So here's my reading for the first non-tensioned wire. I don't think this video is about how to read a vernier, but for those of you who want to check, the vernier is moving from right to left, and I would read that as 828.8 millimetres. So you add the weights and you build up your results. You can see here the beanbag I have to catch the weights should the wire snap. And I think it's quite important for the students to put the weights very gently on the hanger, because once the weights get close to the slipping point of the wire, if they drop them on, the wire will lurch forward and ruin their results. And finally, recording the results does not have to be a massive essay in my view. I've got enough here to draw a conclusion, either by putting the results in a spreadsheet and using the slope function, or drawing a graph in the time-honoured fashion. Drawing a graph in Excel really helps because it does show you where the proportional bit is. And And here is a graph of stress and strain, and you can see you choose the 2nd, 3rd, 4th, 5th, 6th and 7th points for your proportional part in the slope function. And finally here's a force extension graph for Hooke's law, which is a classic shape. I like the way we have a huge extension for the first data point, a nice proportional bit, and then it tails away as the wire starts to slip. So there you are, physics teachers. Thomas WP's take on measuring the Young modulus. Many ways it can be improved, I'm sure. You've obviously got some calculating to do. Young modulus equals stress over strain, or FL over A delta L. But I'm sure you all know how to do that, so I'll leave that. Thanks for watching, and I'll speak to you on the podcast.